Okay, in this video, we'll try to learn how to plot Poisson and Gaussian distribution to fit our experimental data, experimental histograms. So let me share the screen first to show you the origin file. Sharing, origin, share. Okay, so I hope you can see the origin file here. Let's first do the Gaussian distribution. So this is the worksheet for part D of the first part of the lab 3. So this is the counting experiment where we have half a second time interval. The sampling duration is half a second. You can see here the first column in this table. This is the time. Half second, 1 second, 1.5, 2, and so on. And the column B is the actual measurement, is the number of counts we got in this half a second period. So you can see here that the numbers are pretty high, 30, 20, and so on. So that means that the distribution, even though this is an integer variable, the distribution will not be close to Poisson. It's most likely will be close to Gaussian. And indeed, when you plot it in a histogram, this is the corresponding plotted data, the histogram of this data set. And it does indeed resembles more a Gaussian distribution than Poisson. Also, this is a long measurement. We have, how many data points we have? We have 1,200 data points here. And the overall duration was 600 seconds. So it's a 10-minute run with half a second sampling interval, and therefore we have 1,200 data points. Okay, so let's do the following. Let's try to fit it with a Gaussian function. So in order to do that, I first open a new empty worksheet. Okay. This is the new worksheet. Let me remove these unnecessary lines, delete. Okay, so the first one is going to be our x-axis. So this would represent this, this horizontal axis in the histogram. So this is the number of counts, right? The number of counts. Let me assign some random integer numbers running from 0 to, let's say, 50. So for that, I select this column by clicking the left click on the heading of the column. Then I do the right click. Then I select set the column values, set the column values. So set the column values, and it opens this dialog where I can enter the formula, whatever values I want to define in that column A. So let's go, let's define it as I minus 1. So I here represents the number of the line. Okay, the number of the line. So and I runs from 1 to whatever we define here above. So for number of row I, let's go from 1 to, let's do 55. Okay. So that means the first number that will be assigned in the first row will be 0. Okay, so here we go. It created this column. So this is our variable, the horizontal axis. So it runs from 0 to 54. And then for the column B, we're going to define the Gaussian function. Right, the Gaussian function. Now, the Gaussian function, if you remember, it has two parameters in it besides the variable. The first parameter is the standard deviation, sigma. And the second parameter is the mean value. And these two parameters we're going to take from our experiment, from here, because we want to fit our experimental data. So previously in the live video, I show you how Origin can determine the standard deviation and the mean value automatically, and we've done that. It is listed here in this table. So the total number of measurements 1200. The mean value, let me write it down. It's 30.36. 30.36. Right, this is mean, and the standard deviation is 4.9. So sigma is 4.9. Okay, so we're going to enter the formula here for this column B with those parameters. So let's click on the B column header. This is the left click, okay, to select it. Then the right click, go to set column values. Okay, and here we can enter the formula for the Gaussian distribution. So remember the prefactor for the Gaussian distribution is 1 divided by square root of 2 pi times sigma, right? So let me just, keep writing this. So 1 divided square root of 2 pi is simply 2.5. Okay, you can double check, but it's roughly 2.5 times sigma. Okay, sigma in this case is 4.9. By the way, to make sure that the sigma is in the denominator, let me add extra parentheses here, like this. Okay, then this prefactor is multiplied by the exponent, AXP, and here is our Gaussian exponent. So remember how this exponent looks like. It goes like this, minus, then this contains our x value minus the mean value. So our x value is column A in this case. So column A minus the mean value, which is 30.36. And this should be squared. So to the power of 2. Okay. Next, I have to divide it by 2 sigma squared. So divide by 2 times sigma squared. Okay, squared, and sigma is 4.9. 4.9. Just in case, to make sure that it's dividing correctly, let me add an extra parenthesis here. Okay. Just to make sure that this 2 sigma squared is not belonging to this power. So this should be right if I didn't make any mistake. Okay, so let's check this. So let's press OK. Okay, good. So now it calculated all these values. The reason sometimes you get these garbage symbols is simply because the column width is not sufficient. So you have to use your mouse cursor and drag it a little bit like this. So now you have all these numbers. So let's first plot it on an individual plot. So click on column B, the left click, then go to here in this menu, plot, line, line. Okay, this is the plot of this, whatever we created here. So it does look like a Gaussian distribution with the mean, which is close to 30, right? Our mean was 30.36. Good, but this function is correct, but it's normalized as a standard Gaussian distribution to 1. So it's normalized to 1, meaning that if you take an area under the curve, so if you integrate it, you would get 1, which means that the probability of getting any measurement in this entire range is 100%, which makes sense. The problem is that we cannot simply overlay this on top of your histogram here, because this vertical scale here has the scale of this vertical axis is absolutely different from this one. So we have to normalize our Gaussian distribution to your data. And in order to do so, what we have to do is simply multiply this curve, this Gaussian curve, by the total number of data points that we have here in this data set, which is 1200. The reason we do so is because if you take an integral of this histogram, or in other words, if you just sum up all the bars in your histogram, this sum is exactly equal to the number of data points you have in this data set. So that means that the prefactor in front of the standard Gaussian distribution should be 1200. So for that reason, let's go back to this function. Again, select the column, then right click, set column values. So this is our formula. So let's multiply it by 1200. And click OK. So now it should be appropriately normalized. So let me now try to, let me delete this graph, delete. And then I will simply add this theoretical Gaussian function onto our graph with the histogram. So to do that, I select this column B, by clicking on it, left click. Then I'm going to select this graph to indicate where, on which plot I want to add it. So like this, selected it with a left click. Then I go to this menu, graph, add plot to layer, and then select line. Okay, good. So it's edited. So you can see here. Let me double click on this and maybe make it thicker. Okay, so this black line is exactly our Gaussian distribution, our theoretical Gaussian distribution with the experimental mean value and the standard deviation. So you can see that actually it fits our data pretty nicely. Okay, so besides these 2 points that are coming out a little bit, but overall the general fit is very good. So you can fit all your Gaussian distributions in such a way. Okay, and right, so except that I would plot it only from 0. Actually, you can, in Origin, you can select this tool and simply select the data that, only the portion of the data that you want to show, like this. So then you can print it out and you can modify these labels by adding more details. What exactly does it? You can write counts or radioactive counts, and you can print it or save it as a JPEG file and incorporate in your lab report. Okay, so this is the demonstration of how to plot theoretical Gaussian distribution. Let me minimize this. Now let's do Poisson distribution. So for the Poisson distribution, remember that the theoretical form of it is mu to the nu divided by nu factorial times exponent of minus mu, right? So there is only one parameter in it, unlike the Gaussian distribution that had 2 parameters. So Poisson distribution only has one parameter, which is the mean value. All right, so let's start again with a fresh, empty worksheet. Delete this. Okay, so again, first step is to define the X values by selecting this column, then right click, set column values. And again, here I'm going to select enter I minus 1. And for the range, I would use from 1 to, let's say, 10. Okay, from 1 to 10. Now, for instance, this is part F here of our experiment, and you can see that the counting interval here is much shorter. We only have 0.05 of a second, so 500 milliseconds is our measuring sampling interval. That means that the number of counts we're going to be getting for each sampling is very small, much smaller than the previous case. And indeed, you can see here from this data that we have numbers like 3, 5, 4, 2, 1, and so on. So they're very small. And in this kind of cases, when you have integer variable, right, the counts, and the numbers are small, just a few, the distribution would be looking much more closer to Poisson distribution. Okay, so this is the histogram for this data. You can see that indeed there is some skewness in it, so it does look more like a Poisson distribution. Also, in some other parts where the number of counts are even smaller, like for instance in this case, this is the part with flipped source. You can see here that the number of counts is even smaller, 1, 2, 1, 3, 2, 4, 0, 3, 1, and so on. So in this case, it's even more looking like a Poisson. This is the histogram of it. Yeah. So let's feed this with Poisson distribution. So our second step after we defined these columns, actually, let me modify it a little bit. Let's go back to set column values, and I will do it from 1 to 15, a little bit extending the range. Okay. Now let's do the following. So let's use column B to define the factorial of the column A, right? We need the factorial as a part of our Poisson function. And the way to define the factorial in Origin is the following. We have to type this command here, which reads exponent exp of gamma ln parenthesis. Then you have column A plus 1. Okay, let's click OK and see what happens. All right, so again, let's increase the width. All right, so factorial of 0 is 1. Factorial of 1 is 1. Factorial of 2 is 2. Factorial of 3 is 6. Factorial of 4 is, it's 24. Factorial of 5 is 120, and so on. So it looks correct, right? So column B in our case is the factorial of this column. All right. Next step, let's plot the theoretical Poisson function. So let's add another column by clicking this symbol here. Okay, so this is another column. And let's define the Poisson function. Set column values. Okay, so the first term is the mean value mu to the nu. Nu is our variable. Mu is the mean value. So let's first check what our mean value was for this. We have to work with the mean value that corresponds to this experiment because we want to feed this data. So previously we determined this by using the standard origin function, and the results here. So again, in this case, you can see that we have the total number of data points is 1200. The mean value is 2.996, basically 3. We can round this. Okay, so the mean value, let's say, is 3, which is our mu. And the standard deviation, well, actually, standard deviation is not included in the Poisson function. Okay, so let's go back here, set column values. Now the first term is mu to the nu, right? So mu, the mean, is 3 to the power of column A, right? Because column A is our new value, the integer variable. Good. Then we have to divide this whole thing. Oops, sorry. Have to divide this whole thing by the factorial of nu. And factorial of nu, we calculated it in our column B. So let's divide this by column B. Okay, so column B is already the factorial of column A. Let me double check this to the mu. Right, divide by the. Okay, since looks good. Now the next, the last term is we have to multiply this whole thing by exponent to the power of minus mu. So I will need extra parentheses times exponent to minus 3. Okay, because the mean value is 3. And let's say, okay. Okay. So here's our Poisson distribution. So first, let's plot it on a separate plot. Left click on the column C and then go to plot, choose line. Here we go. Okay, this is our Poisson distribution with the mean value of 3. Okay, let me delete this. Delete. Now we want to plot it on top of this, but again, we have this problem here is that the standard Poisson distribution is normalized to 1, while our data have very different vertical scale here, right? So the trick is the same, because the net sum of this histogram should be exactly equal to the number of data points, of which we have 1200 in this case. Then we simply need to multiply our Poisson function by 1200. So let's go back to the definition of this column here and let's multiply it by 1200. Okay. So now we should be able to plot this on top of this histogram. Okay, so let's select this column C by left click. Then you go here, select this graph by left clicking on it. Then go to graph, add plot to layer line. Okay. So let me increase the thickness of this line, let's say to 3 and maybe change the color. Okay. All right, so this green curve is the theoretical Poisson curve for this case. There is some similarity. It's not a perfect fit, but nevertheless. Let's repeat this for this case here, for part with the flipped source. Okay, so for this part, let's first determine the mean value. Let's select this column. Then we go statistics. Oh no, actually we use right click. Then we go statistics on columns. Okay, it's adding this information here in the extra tab. All right, so the mean value is 1.55. Okay, 1.55. 1.55. So let me use the same worksheet here for Poisson distribution, and I'm going to add an additional column. And then what I'll do is this, I'll copy that formula that we had here. Set column values, use this, copy, cancel. Then I'm going to define this a similar function here in the new column. Paste. Now I have to remove this 3 and replace it with 1.55, which is the mean value for this part flipped, right? So 1.55. Okay, so this is our distribution. An additional thing, let me double check how many data points we have here in total. Oh, we actually have it here. Well, it's 200. Yeah, it says here it's 200. So I'll have to change the prefactor. This prefactor, instead of 1200, I only have 200. Okay, all right, so here we go. Now let's add this D, this Poisson distribution for this case to this data and see what happens. Okay. Yeah, it has some resemblance. Okay. Actually, you can see here that the for the Poisson distribution, it's not really a smooth function, even though we're plotting this as a smooth function. In fact, it has only actual values for the discrete integer values of the variable, for 0, for 1, for 2, and so on. So the actual data points, let's plot it as data points. So instead of just line, let's use line plus symbol. And for the symbol, let's choose circles, maybe a little bit increasing the size. Okay. Right. So the what matters is only these data points, the black circles here. The straight line doesn't mean anything real. It's just we're connecting them by origin. So you can see that the height of each bar is roughly represented more or less correctly by the Poisson distribution in this case. Although this one is a little bit, the second one is a little bit, well, it's probably within an error. Yeah, so it looks like it is representing more or less correctly with the Poisson distribution. Okay, so additionally, you can also do this exercise, which was offered for an extra credit by doing similar procedure, where you were supposed to put on the same plot several Poisson distributions for gradually increasing mean value, going, let's say, from mu equals to, let's say, 0.5, increasing it gradually all the way up to, let's say, 10, and observing that the shape of the distribution changes from Poisson to Gaussian. So let me, okay, let me do it here again. So I'm gonna add an extra column, right? So this one was, the column D was the Poisson distribution with the mean value of 1.55, which looked like this. So let's simply copy these values, copy, so then set column values, paste. Let's do it with 0.5 for the mean value. 0.5. Okay, and let's plot it on a separate plot. Plot line. Okay, line. Okay, so this is the Poisson distribution for a very small mean value, 0.5, right? So let's add more. And let's do it for 1, for the mean value of 1. Okay. Let's add it on the same plot. So again, how to add curves to the existing plot. So again, you click, left click on the column heading to select it. Single click. Then single left click on the graph, like this, to select it. Then you go to graph, add plot to layer line. Okay, so the this one is this one is for the mean value of 1. Then let's continue, maybe a couple of more. Set column values, paste. So, well, we have 1.5, right? So let's do, I don't know, let's do 2. No, let's do, yeah, let's do 2. So the mean is 2, okay. For definitiveness, let's add this one, which is the mean value is 1.55. Let's add it here. Line. Okay, so this one green. So the green is the mean value is 1.55. Let's add this one, which is the mean value is 2. Line. Okay. So this value, this one is, let's use blue. Okay. So let's add maybe 1 or 2 more. Set column values, distribution. Let me use something much greater. So we had 2, right? So let me use 5. Okay. Line. Okay, so this is Poisson for 5, for mu equals 5. And let me do just one more with a really great mean value, like 10. Paste. And here I would have a 10. Okay. Graph and plot layer line. All right. Cyan, I don't like to use cyan, it's not dark enough. Let's use magenta for this. And for the 10, I'm gonna use orange. Okay. Well, you can see here that indeed the Poisson distribution transforms gradually into something that looks much more like a Gaussian. Our data are cut here at 14, which we can fix easily. Let's go back to this data set and let's increase the range here. So set common values. We can go from 1 to 30. Should be enough. Okay. And automatically it recalculates everything. And here you have more extended data. So to rescale this whole plot, click on the plot to select it, then go to graph, rescale to show all this. Okay, now it's rescaled. And you can see that this orange curve, we can again use this magnifier here to select only this data. Like this. So you can see that this orange curve indeed looks much more like a Gaussian. Rather than Poisson. That's because it corresponds to the mean value, which is pretty high, 10 in this case, right? Okay, so let's rescale. Graph, rescale to show all. And you can see that for really small mean value mu, it does resemble more of a Poisson distribution. So we can magnify this where you can see this. So these are more Poisson. Okay. So when you plot them on the same plot just for theoretical analysis, you don't need to normalize them. But if you want to overlay these theoretical curves on your experimental data, those histograms, you will have to normalize these curves by the total number of data points in each histogram that you have. Okay, so I hope this explains how to do these plots in Origin.